Okay, so this is basically the intro. So far we've talked about sequences, was what just like we're taking it to be just a list of numbers. Right? And we can tell if that list of numbers converges by coming up with a formula that describes this list and taking the limit of the formula. When we're looking at series, what we're doing is we're adding all these terms together in the sequence, and we want to know, does that add up to some finite number, right? And when a series does add up to a finite number, we say the series converges, right? And we've also shown that the series converges if the limit of its partial sums converge, right? That's another sequence. In general, though, finding the sequence of partial sums is super hard. And we've done also telescoping series, but of course not all series are telescopic. So now the question is, in general, how can you tell if a random series that I give you, if it converges or not? And that's what these series tests are for, right? These are called convergence tests for series. It's in the table that I handed out in class a few days ago. Right, so we're just going to go through all these tests, and I'm going to show you when you can use them, show you some examples of using them. And yeah, these tests will really cover everything we're going to do in this class. It's not an exhaustive list. There are tons of tests that are not in this table, and tons of series that we won't be able to work out with this table. But in Calculus 3, pretty much everything you'll get, you'll be able to use one of these tests to deal with it. So that's where we're going today. We're going to figure out how to find out if a series converges if I don't know what its sequence of partial sums look like. sums look like, or it's not telescoping, right? Like in general, how do I know if these series add to a number? Right? And that's where we're going. So in our table, telescoping series and the first two tests falls under 8.2. So once I finish the kth term test, that will actually cover everything you need to know for telescoping, right? And then we're going to continue. Okay, so let's begin there. So we've already seen telescoping, so now the next series that is a very common type of series is the geometric series. So as you can see in our table, it tells you there's a when to use column, right? So you can sort of look at that when to use column, and it will tell you an example of when you'd want to use this test, right? And it says anytime you have a series that looks like this, right, you can use this test, right? So if, let's see, that's the form AR to the n, goes from 0 to infinity, or AR to the n-1, and it is a geometric series. Now with geometric series, we actually can tell exactly when it will converge, and we even know in this case to what it will converge. This converges to A over 1 minus R if your R is strictly less than 1 in absolute value, right? i.e. R is between 1 and minus 1. Diverges so that's a geometric series. Pretty much anything that looks like that is a geometric series, right? So basically if you see that form, it's a geometric series, and you can tell whether it converges or not based on what values the R actually takes on, right? So A and R are constants, and is the variable, and your R, once it's a constant somewhere between -1 and 1 strictly, it will converge, and it converges to this number, right? So you can tell that it converges and what it converges to. Otherwise, it will diverge. So let me show you an example of that. It's hard to come up with a hard example for geometrics. They usually come in handy when you're doing comparison tests. But let me give you a relatively hard example for this. For this one, it's not hard because it's just you see that form, you apply this form. That's easy, right? And you can actually prove that this will converge to that. You can look at the sequence of partial sums. You can actually figure this out, or you can even use algebraic manipulation, right? I'll probably show you the derivation for that later, but probably yeah, because we're actually going to look at that again. But maybe later I'll show you how to derive that. It's actually not hard. So let's look at an example. So I gave you that series, right? Can you tell me if it converges or diverges? How about A? It turns out that these guys are geometric series. In fact, they're sums of geometric series. Anyone has an idea of how to show that? This is 1 plus e to the n over 4 to the n plus 1.
That converges.
We can separate.
This converges, right, but you can separate it first. This is 1 over 4 to the n plus 1 plus e to the n over 4 to the n plus 1. Okay. But you could in fact separate these into two series. Now, how do you know that those converge?
Because e to the n is always going to be greater than 4. 4 to the n plus 1 is always going to be slightly greater than e to the n. So it's going to go.
Well, here's the question. Do these converge? If so, to what?
So we have to figure out the A and the R.
You have to figure out the A and the R, yes.
We have to bring
So you
them
can use
into
that.
4 and 1.
So we have to write this to look like that. Exactly. How do we write this to look like that?
ln.
A is just the first term.
Huh?
Yeah. A is just the first term.
No.
A is just the first term. What does it look like?
We make
Equals 0. That n equals 0. You'll get what? 1/4. Then you have 1/4 over 1 minus the ratio. And the ratio, if it's 1 over 4 to the n, or 1 over 4 to the n plus 1, you're just multiplying by 1/4 every time. So that's 1/4 over 1 minus 1/4. 1/4. It's like a third.
Yep. So what he says is basically you can think of A as the first term in the sequence. R is the so-called common ratio. So then that comes in handy. For example, you're given a list and you want to figure out if the list converges. Common ratio means your a n plus 1 divided by a n is a constant. All the way to R. In this case, you don't have to do that. We could actually rewrite this clearly. Because 4 to the n plus 1, you can just write as 4 times 4 to the n, right? So this I can really write as a quarter times 1 over 4 to the n. Similarly, this I can write as a quarter times e to the n over 4 to the n. This means I can write this as 1 over 4 times 1 over 4 to the n. Plus this, I can write as 1 over 4 times e over 4 to the n. Which means for this one, your a is 1 over 4, your r is 1 over 4. Here your a is 1 over 4, your r is e over 4. Here, your r is less than, it's in the range that we like, right? It's between minus 1 and 1, which means this does converge, and in fact it converges to that number. So it converges to a over 1 minus r. Plus. Here a is this, r. Does r fall within our range?
Yeah.
Yeah, what's e?
Like
2.3.
Right, e is 2.7, right? 2.7 something. 2.7182818.
3.
Right? So it's 2 point something. divide by 4, you definitely get something less than 1. And so this also converges, and it converges to that formula. You take the A divided by the 1 minus R. So this is going to be 1/4 divided by 3/4 plus, this is 1/4 minus. So this is 1/3 plus. So that series does converge, and it converges to that number. Now if you look at this one, you can try a similar manipulation. We can actually write this as your log. This would be 1/3 times 2/3 the n plus right. Similar manipulation to what I did here. Right? In this case, your r is 2/3. That falls between -1 and 1. So this guy actually converges. So here your A is 1/3, your R equals 2/3. This guy converges. Over here though, your A is actually 1/3, your R is actually 5/3, which is bigger than 1, right? So what that means is this guy diverges. In fact, it diverges to infinity. So this means overall, a part of it converges, but a part diverges. So you have a finite number added to infinity. It still goes to infinity. Right? It's very similar to back in calc2 when you were doing improper integrals. You split up an improper integral. Part of it converges and part doesn't, then the whole thing diverges. Yeah, that's the geometric series. Basically, you try to write it in that form. If you sort of see it, you can write it as something like this. You can apply the geometric series. So as long as your r is between -1 and 1, it converges. If it's not, it diverges. And that's basically it. That's the geometric series. Any questions on that? So in general, it's not hard to apply. So what they're going to do is they're going to give you something where you have to do a lot of algebra to get into a nice form to apply it, because there's really no way to make this more difficult other than doing that. Now they introduced the geometric series first in this list because it's something that you would have seen before in previous chapters. But really the kth term test is the test you probably try to apply it first, right? So this is a kth term test, aka n term test, aka test for divergence. So basically what this test tells you is it can tell you if something diverges. Yeah. Oh, yeah.
Sorry, just a quick question about that one. So if R equals 1, then it also converges?
R equals what?
So if R equals 1, does it also converge?
No.
It doesn't, so that also converges?
Yeah, it has to be strictly between -1 and 1 to converge. Okay, back to the K-term test. The K-term test is called a test for divergence because that's the only thing it can tell you. It can tell you something diverges, right? It can't tell you if something converges. So And it's pretty much just taking the limit of the guy. Right? So 1. So the geometric series test had a special form that you can use it on. The K-term test, you can use it on anything, right? Can be used on any series. And it's actually the first test you should think of applying. The good thing is it's usually easy to see if it would work or not, so it's the first thing you should look for. And because it's usually the computationally easiest. So the test says if the sum of an given sum of n, this guy, limit of the an is not equal to 0, then the series diverges. Called the test for divergence because it can only tell you about divergence. You cannot use this to tell if something converges. Right? There are many examples of series that you can use where the limit will go to 0, but it doesn't converge. The most famous example of that is the harmonic series. Very important series. It's the guy that looks like 1 over n. As n goes from 1 to there are cases where the limit is 0, but it doesn't converge. So be careful of that, right? This can only tell you about divergence. It cannot tell you about convergence, right? So if anyone tells me the n-term test and they say, oh, it converges by the n-term test, you don't know what you're talking about. I'll just give you 0 and move on. Right? So it can only tell you about divergence. And the idea is, for a series to converge, right, you're really adding an infinite number of terms. So basically what has to happen is eventually it has to be like you're adding nothing for something to converge, right? If you're always adding a positive number, then you always keep getting bigger and bigger and bigger. The idea is you want something to get, eventually it's like you're adding nothing. So the limit of the terms goes to 0. So eventually some part way out in infinity, right, you're adding something that's pretty much 0. And so that's why your guy will converge. However, sometimes you don't get to 0 quickly enough, in which case this guy doesn't get to 0 quickly enough. So by the time you're getting super small, you already added too much. Right? It's sort of weird to think about it for infinite sums, but that's sort of what's going on. This guy doesn't go to 0 fast enough. Right? So you keep adding things that are too large. But other than that, you can actually apply this test pretty easily. So for example, let's say I have the series and it goes from 1. You're given that. Does that converge?
Yeah.
It converges. Here, an would be what? 3n squared plus 2n plus 1 over 4n squared minus 3. So the limit of an is what? What's the limit of this? 3 over 4. Which is not 0. Therefore, series diverges. That's it. So one's the easiest test to apply because it relies on a single variable limit, which you guys are all experts at now. So if you can look at something, you can tell, oh, the limit's not 0. You don't have to do anything else. It diverges. Yeah.
This was a sequence. Would it converge to 3 over 4?
If it were a sequence, you would say it converges to 3 over 4. Yes. But as a series, that's bad. It means that as you go up to infinity, you keep adding things that are around 3 over 4 big. You'll never get to a finite number because you're always adding 3/4. Right? You go to infinity. That's it. Limit's not 0, diverges. Right? Can't tell if it converges. Okay. So if this were a cube, the limit would be 0, but it would actually still diverge. Right? And we're going to do tests to show you that later on. But that's it. And that actually finishes 8.2, by the way. So if you want to get ahead on homework, you can start 8.2. Let's move on to the next test. Any questions on this, by the way? So this is called the test for divergence, or the nth term test, or the kth term test. Warning. It says the converse is not true. Right, meaning the reverse. The reverse statement is not true. So it says the limit is not 0, it diverges. It's not true that if the limit is 0, it converges. That's not true. Now we're going to do an integral test, which is also a test that's easy to apply for you guys, because you're all experts at this. Integration, right? Integral test. Now here there are some restrictions, right? Remember that when to use column? That tells you what the restrictions are, right? So suppose you have a series of a to the n. I'm using n even though this uses k because your textbook uses n. So everything else is good. It's just a W. Then this guy, convergence. That's not a typo, by the way. That was intentional. This is it, and that means it works in both directions, right? So if you know one converges, you know about the other one automatically, right? But there's a restriction on this, provided greater than or equal to 0. And decreasing, I think, is usually. Which means if you see a random series and the limit goes to 0, so you can't use the test for divergence, it's not geometric, so you can't use a geometric series. One thing you can look at is look at the actual function itself. If it's continuous, decreasing, and always non-negative, and you can integrate it easily, you can do this test, right? So use if the above are satisfied the test for divergence does not work, and AN is easy to Now the reason this works is sort of because of the sort of because of the comparison test. The idea is that this will actually always be true, right? Because a series, if you're looking at some random function, the series sort of adds up. Right? It only works on the integer values, right? Where if you're taking an integral, it'll work everywhere, right? So the integral always actually gives you a larger value than this guy does, right? So if this is a finite value, then surely that's a finite value because it's going to be less than, right? That's the idea. The proof is more involved, but that's the idea behind it. So that's the integral test. So let me give you an example of the integral test. By the way, the text and the table will say decreasing, but it's actually good enough if it's eventually decreasing. So if it has a rocky start where it bounces up and down, but eventually it just keeps decreasing, that's okay too. Yeah.
Or when you do the summation, right? And let's say that's a product of two functions. Is that product, is that sum the product of two sums?
Not in general.
Not in general.
Right. Especially in this case, the product, the function would be 1 over n times 1 over ln n. Each of them actually diverge.
Would that be series divergence?
You can't tell from that.
Oh.
That's only true if each would converge on its own. But even if that happens, they don't always go to the same number. It'll be the difference like between raising a sum to a power, right? If you multiply all the terms together, it's sort of like you can write this out. The difference will be this, right? So the one where you can separate them would sort of behave more like this. There'll be extra terms as opposed to this. I mean, if you write it out, you'll see. So in general, you can't do like a product rule. However, here, if I take f of n equal to 1 over n L of n, then notice that f on this interval is actually continuous because I never divide by 0. It is also decreasing, which you can easily see because the top is a constant, the denominator keeps growing. Right? Actually, one more. This guy converges. And now we get, if I take the integral from 2 to it's going to be a 1 over n L n. But what is this integral? This you get ln of ln into infinity, right? Fraction diagram. Just made that one up on the slide. Pretty sure it's a homework problem. That's a pretty typical problem.
Did you guys like
What? U substitution. U equals ln n. No, u equals ln n. Du would be 1 over n, so you get 1 over u. You get ln u, but you use ln, so it's that. Yeah, it would be a u sub. What about this one? Again, notice here, as your n gets bigger, the power would go to 0, right? Which means the top is going to 1, whereas the bottom is going to infinity, right? So this is an eventually decreasing thing. Of course, the exponential is continuous and n squared is continuous, so the ratio of two continuous functions is continuous as long as the denominator is not 0, so it's also continuous. And of course, each are positive because it's an exponential and n squared, so it's always non-negative. This is continuous, decreasing, non-negative. is the integral from 1 to infinity of e to the 1 over n squared n. This is equal to minus e to the 1 over n. And then you would plug in infinity. 1 over infinity is 0, so e to the 0 is 1. And this here is converge. It doesn't converge to that number. This is actually an upper bound for what it would converge to. But if this converges, the other one would. Notice here in particular also that our test for divergence would not work, right? The limit of this as n goes to infinity is 0. The limit of that as n goes to infinity is 0. So the test for divergence, if you applied it here, it would tell you nothing. And so you realize that, oh, well, these are continuously increasing greater than 0, and they're easy to integrate. They're easy substitutions, so you just apply the integral. Yes?
So for these type of questions, you will not ask us what it converges to because
No, like this I wouldn't ask what it converges. So in general, I will ask questions like are on the final, which by the way, I already put up the review for the fourth test and the final. So in general, the ones on your fourth exam would be, tell me if they converge absolutely or conditionally, right? You won't always be asked to say what they converge to, because you won't always have all the tools to know it. So I just know it converges. To what? I'm not sure at the moment, but I know it converges. That's the integral test, right? So your test for divergence doesn't work. Your function satisfies these conditions, and it's easy to integrate. Try the integral test, right? So you're always looking for certain patterns to arise, and that sort of tells you when you can use a certain test. So you just follow what's in the middle column, and that'll tell you, okay, when do I use this? But the test for divergence is always the first thing you check. Yes? The derivative would tell you about this guy if you're not sure. Right. So if you're not sure about the decreasing power, you can use it. You take the derivative, and if it's negative after some point, it's always negative, then it will tell you about this. But other than that, the derivative will always tell you. The derivative can help you figure out if things are decreasing. Yes. Another very famous kind of series is the P series. Just like the geometric series, it refers to series that have a very specific form, right? A series of form 1 over n to the p is called a P series. Notice P is a constant. This guy converges if your P is bigger than 1 and diverges P is less than 1. So that is called a P series. I'm not sure why they use P, but they always use P. They call it a P series. P is the generic constant. So examples of that again, here it's never going to really be hard to apply this. It's sort of, you're going to be applying this test while applying another one, because here, it's just knowing a certain form. So, example of the series. What?
Yeah. Otherwise, that means the harmonic series.
P is greater than 1, you should diverge. And P is less than 1, you should converge.
Nope, that's right. Yep, that's right. So the harmonic series has P equal to it, so it diverges in that case. So again, look at test for divergence. It goes to 0. So can't really tell me anything. So it is decreasing and it is easy to integrate. So I could actually use the integral test here, but we already finished that section, so we're going to use something else. But the integral test could be something we could apply, but I'm not going to. We're going to do the P series because I notice it's actually going to be a lot easier to notice that this is just 1 over n. This is a P series with P equals a half less than 1. That's sort of. It gets more exciting when you have to apply several tests at once. For now, it's still. This, you can realize that this is just 1 over n to the 11 over 10. This is a P series with P equals 11 over 10, which is greater than 4. Series. So in general, you can actually prove the P series test using the integral test. You'd realize that if you take the improper integral of 1 to infinity of that guy, it will diverge if your P is greater than 1. It will converge if your P is greater than 1, diverge if P is less than 1. And you can sort of try it. Right? So, yes.
Why is it you're not writing integrals without the sign?
N equals what?
The limit.
Oh, I mentioned that. It's just me being lazy. That's should be understood. Especially if there's no other variable present, you would assume n equals. I mentioned that the first day, that sometimes I'll get lazy. That's sort of it for P series. They don't really get much harder than that. The next thing in this guy is the comparison test. And you can sort of think of the comparison test. Or improper Back when you were doing improper integrals, there was also a comparison test. The same sort of thing works here, right? Because you can use the integral test to show if your improper integrals converge, then your series will converge. And so you can sort of apply the idea here, right? Everything is just less than they would have been in your improper integrals comparison test. But the comparison test says the following. Given series A n and B n with then if Bn converges, then An must converge. It has no choice. And if An diverges, then Bn must diverge. Yet no info from any other for this test. That's it. Once you can set up this inequality, you know two things. If the series of this guy converges, because, and this is because of something I told you back on when we just started series, this would mean that the series of An is less than or equal to the series of B. Right? So what that means is if this guy converges, meaning he hits a finite number, then this guy would have to hit a finite number as well, because it has to be less than or equal to that guy. So if this converges, it forces that to converge. Right? Also, if this guy diverges, say goes to infinity, then this guy would have to diverge as well. Because it would mean this guy has to be bigger than or equal to infinity. So he would have to go to infinity, right? So if the bigger one converges, the smaller one must converge. If the smaller one diverges, the bigger one must diverge as well. Otherwise, we can't really use this test. We have to use something else. But this is just by comparing the sizes of the terms, we can talk about their series, right? So in this test, it is important to know so you have to know who's your A and who's your Bn, and then you can apply this test, right? And you have to know the order of the inequality. Give you an example of that. So in an exam, you get that series, right? Which is a lot easier than any series you'd actually get here. Let's suppose you get that one.
Thanks.
So what's the first thing you're going to do? Test for divergence, right? But the limit is actually 0, so test for divergence doesn't help. Okay, what else can we do? E series doesn't look like an E series. Integral test? That's not easy to integrate at all, right? So what?
Square everything?
You can't square everything, you'll change the value. Right? So at this point, it turns out that we can actually use the comparison test. because I know how to figure out a fraction that's actually, notice that, this guy is greater than or equal to 0, correct? Right? Now if I make the denominator smaller, I know in a fraction if I make the denominator smaller, the fraction gets bigger. K is 0 or positive, right? Which means 2k plus 1 is always positive. Which means if I remove that, I get something smaller. This is actually less than or equal to 3k over 3 to the k. Join this. Typically speaking, the highest powers are really the guys who control the whole function. So you usually want to get rid of everyone except the highest powers anyway. Right? So what I did was, I made the denominator smaller so it gives me a bigger fraction. But it turns out that this guy is actually equal to what? It's actually 3 over radical 2 times k over k to the 5 over 2. This is actually 3 over radical 2 times this is actually 1 over k to the 3 over 2. Right? So take an equals that 3 to the k over 2k to the 5th plus 2k plus 1, and your bn to be this guy. Bn converge or diverge? Converges by the p-series test, right? By the p-series test. Now things are starting to get a little interesting. You have to apply a couple tests at the same time. That's actually pretty typical, right? So I do this manipulation to get something that's bigger, and I know that that converges because of the last test that we did, the p-series test, right? Which means an converges by the comparison. And this is actually typical. In general, you won't be given both an and bn. They're not going to tell you what the an and bn are. You're just given a single thing, and you have to figure out something bigger than it that converges or something smaller than it that diverges, right? So here, I did this, and it was, okay, get rid of the lower powers, right? I get that. And I know that that's bigger, and I know that it converges, so I can use a comparison test. Right? If I got something bigger that diverges, it wouldn't tell me anything. Right? But here it actually worked out pretty nice. Got something that's bigger, that guy converges. How? By the previous test that we did, p-series test. Which means that this guy converging forces that guy to converge because the series of this has to be less than the series of that. That's a comparison test. example of a comparison test that converges. What else do we have? Here's another test. So the comparison test is nice, but you actually have to know about that inequality, right? You have to know that there's an AN and a BN and which one is bigger, right? There are cases where you want to use a comparison test, but then when you actually tweak your function, you're not sure if you got something that's bigger or smaller, right? In that case, you can use the limit comparison test. So this is like a comparison test, but you don't have to know how the inequality fits together. You can still use a comparison. So let me give you an example of that. Oh, I never actually said what the test says. Let me write that down. Okay, so I mean, it says it here. What this test tells you is that your two series under these conditions would actually do the same thing. So again, you're going to be given one series. You have to tweak the formula to come up with another one. It doesn't matter if it's bigger or smaller. You can apply this test. The trick is, the new thing that you obtain, you should know if it converges or not, right? And then you can actually apply this test to tell if your AN will converge or not. Right? If this is true, then both your series actually do the same thing. So if your new series converges, this will have to converge. If your new series diverges, this will have to diverge. Right? This means that their growth rates are pretty much the same. They're just, the growth rate of one is just a constant times the other one. So that's how it works. So let's do an example. given that series, first thing I try to do, test for divergence. But the limit is 0, so that doesn't work. What else could I do? Well, it's not a P series. So what else can I do? I can try the integral test, and in this case, the integral test would actually work. You can integrate that, right? You can do a u sub on the bottom, u equals k squared plus 2k plus 3, right? Your d would be 2k plus 2, right? You can factor out the 2 and get that k plus 1, which gives you the top. So the integral test could work here. So the integral test could work, but pretend it didn't, right? Like, I could have easily messed that up. Could have made this a cube. I could have made that a different constant, in which case it won't be easy to integrate because I have to do all these manipulations. Right? So here what we can do then is we can say, okay, comparison test is the next easiest test to apply, right? So let's try to apply the comparison test. Which means this is an AN, I'm going to try to figure out my BN, right? So that's what I'm going to do. So what we would do is, so from this guy, a plus 1 over k squared plus 2k plus 3, we would go to something like this. Right? Now the question is it this or is it that? Right? Now, to go from this to this, I actually made the denominator smaller, right? So the fraction would be bigger if all I did was change the denominator. However, at the same time, I made the numerator smaller, which means that fraction would be made smaller if I made the numerator smaller, right? So I both made it bigger and smaller at the same time. Which one wins, right? So we could go and try to figure out, okay, would this actually be bigger or smaller? But then that might take too much time, right? And especially since this is a very easy example, it would probably be a lot quicker here than in general, right? So I did this manipulation to get something easier, and I'm hoping that would be my BN. The thing is, I'm not sure if it's bigger or smaller, right? Because I did things that have opposite reactions, right? Changing the denominator makes it bigger, but changing the numerator this way makes it smaller. So who wins? I don't know. With the limit comparison test, I don't care. That's actually the idea, right? So I did this, not sure whether the inequality points, that's fine. Don't use the comparison test, use the limit comparison test. Take AN equals k plus 1 over k squared plus 2k plus 3, and BN equals k over k squared, which is 1 over k. Then the limit as k goes to infinity of a, k, well, these are actual k's. AK over BK. This would actually be k plus 1 over k squared plus 2k plus 3 times k over 1. Right? Now that limit is what? What's that limit?
That goes to 0.
Huh? It's 1. Come on, my calc2 geniuses. So that limit is 1, which is actually greater than 0, and of course finite. Which means the limited comparison test applies. It's also the case that both of these are always bigger than 0 when my k is bigger than 3.
When your k is bigger than what?
Bigger than 3.
Okay.
Right? When my k is bigger than 3, this guy's positive and that guy's positive. So according to the limit comparison test, what can I say about my original series? This means AN and EN would be the same thing. But sum of DN is actually 3 to infinity of 1 over 2, right? Which is a divergent thesis. It's not strictly harmonic because it doesn't start at 1, but it's essentially harmonic, right? So I actually know about the Bn, right? That actually diverges. This is AN. So the limit comparison test is a test that really comes in handy when you want to do the comparison test, but you're not sure which way the inequality points. If you're not sure where the inequality points, just do this. And hopefully you get a finite number that's positive, in which case you can know what one series will do based on what you know the other one will do. Yes?
Why aren't we so sure about the inequality?
Because I made the numerator smaller at the same time I made the numerator smaller at the same time I made the denominator smaller.
Oh, so you switched two things instead of just one.
Yeah, I changed both the top and bottom. Right? So, I mean, the top is smaller, so the fraction should be smaller, but then I made the denominator smaller as well, so the fraction should be bigger. Right? So I made two changes that have opposite reactions. So other than trying to sit there, you know, rip my hair out of my head figuring out which one wins, I can just employ the limit comparison test. Yeah, so that actually does it for the limit comparison test. That's what you need to know. And this finishes. Now we'll take a 10-minute break and go to the next one. Okay, let's jump back into it. We're jumping into 8.4 right now. And it begins with the alternating series test. In this case, alternating refers to the sign, right? So if you have a series where the sign alternates, you have, say you have an alternating series. So it looks something like something like that, right? Where we've seen this minus 1 to the n guy before, right? So this is just something that alternates the sign, right? So whenever n is odd, you get negatives. Whenever n is even, you get positives, right? So you just get a plus, a minus, a plus, a minus, a plus, a minus. Whenever you have this guy, you say you have an alternating series, right? And the power doesn't have to be n. You could see an n plus 1 or n minus 1, but as long as you realize that the signs alternate, that's the important thing, right? That is called an alternating series. And when you have series like that, they have their own test. Okay. So where are we? Suppose n is and that's the test. If all your terms are positive, they're decreasing, and they decrease to 0, then your series will converge. Right? Now, there's a simple but very important example. Is this guy. This is called the alternating harmonic series because it's actually minus 1 to the n times 1 over n. Now we know that 1 over n actually diverges because it's a p series where p equals 1. But it turns out with the alternating series test, this series actually converges. that series actually converges, even though its positive counterpart diverges. Right? This is very important for also the next topic, but it's also a very important example of how things can change when you change the sign. Right? Turns out if you subtract every other term, this thing will actually converge. In fact, it converges to ln2, which we will be able to prove later. Actually, it's this guy that converges to ln2. I had something wrong in my notes. It's still alternating, but that's the one that converges to ln2. You start with a positive term. +1 and -1/2 and +1/3 and -1/4.
Can't you,
Yeah?
you could also just write it from n equals 0. Oh no, you can't.
Right, no, because the denominator.
Right.
That's a super important example. That the alternating harmonic series converges while the harmonic series diverges.
Is there like an order where like certain tests, like their results, are like more conclusive than the other ones? Like if it doesn't.
No,
work
if
for-
one works, that's good enough for me.
Yeah. Okay.
If you can apply it and it works, do it. It's fine. They're all proven to be strong enough, right? Any one test, you have it, you have it. And you don't say, oh, I proved this using alternating series test, but I don't trust it. Let me use any other test. No, if it works by this, it will work with the other one as well, as long as it can work. Right. Yeah, did I have another example? I have another one. It's very simple. Oh. Put another one. I just made that one up. I should probably put in these in my notes. Put a bunch of random ones back in the other class too. I should probably write those down. Okay. Now, here, when you're looking at AN, you pretty much ignore the alternating signs. So here your AN would be this guy. AN greater than 0, or N greater than equal to 1, and then is decreasing, and the limit of AN equals 0. So it converges. What if it wasn't alternating? Would it converge then? Who thinks it would converge? Converges, right?
Yeah.
Does it converge? he thinks it converges, and Eddie thinks it converges. He's a camera girl, so she should be right. It actually diverges. You can use the limit comparison test to prove it diverges. Right? So if you do this, you take away that 1, which means you make the thing bigger.
Oh.
Right? However, that's a divergent p-series, so the bigger one diverging doesn't really tell you anything. But you can actually do the limit comparison test, and the limit would give you 1, right? And so then I know that since the other one diverges, it would. So you can actually prove that without this, it will diverge. And there's a special name for series like that, right? When they're alternating, they work, but when they're not alternating, they don't work, right? We're going to talk about that in a minute. And that's another reason why this is super important. Because if it's not alternating, it doesn't work. If it's alternating, it works, right? And those series are really funny guys. You're going to see some. Here, how would I know about this one?
You factor out the 3.
I can factor out the 3, so this would be 1 to the n, 3 to the n over n plus 1. Now what?
Oh.
Now what?
Same thing?
Yeah?
No, it's
Even though a to the n is positive, it's not always decreasing.
It's not always
Because
decreasing,
we know
that's
that
correct.
we
In
need-
fact, most of the time it's increasing.
Yeah.
Here, and it's even simpler than that. Test for divergence would also work. Limit of an is not equal to 0, so it diverges. Right? So if you can use the test for divergence to show it diverge, or you can say since an is not decreasing, diverges by alternating series test. So it's not unheard of to have several ways to prove something diverges. Right? So here, with that out of the way, when I can see my n, oh, that limit actually goes to infinity. Right? 3 to the n is an exponential over a radical. Right? The top wins. So that limit actually goes to infinity, so the test for divergence show it diverges. If you're partial to the alternating series test, which I don't know, it's up to you if you want to be, then you can see that that is actually not decreasing. Right? So just the little innocent maneuver like putting the 3 inside here actually completely changes the answer. Right? So it's very important that you're very specific and pedantic when you're applying these tests, because any little thing can mess everything up. Sometimes making it alternating messes things up. Well, it can make things better, while otherwise it messes things up. Right? So be careful. Okay. Something else about the alternating series. It's going to help us a lot later when we're trying to evaluate certain integrals. There is something called the alternating series estimation theorem. Suppose you have a convergent alternating series, right? Converges to some number s. We may or may not know what this number is. Right? But for example, I can know that the first one over there converges, but I don't know what number it converges to at the moment, right? But let's say I just know it converges. Then it turns out I can actually estimate the answer within any desired range of accuracy. Then So a really neat thing with alternating series is that you can actually approximate the nth partial sum's accuracy with the n plus first term, right? It will always be that distance away at most from the actual answer. Right? So, for example, let me do an example to show you what I'm talking about. Example. Look at our famous example, the alternating harmonic series. A how good an approximation is S2 to the actual value of series? How many terms of the series are needed to get to approximate the sum to within 1/100th of its actual value? That's actually the question. That's the question. So I know this thing converges to something. I'm not sure what at the moment. We haven't covered what we need to know how to prove it, right? But I know it converges by the alternating series test, but converges to what? Well, I don't know how to get to the answer yet, but it turns out I can actually approximate the answer. I can get within 2 decimal places if I wanted to, or 3, or 4, or 5, or 6, or 7, right? Any desired reason, any desired degree of accuracy, I can actually get there with an alternating series. All I have to do is to look at the very next term. The very next term actually tells me how close I am to the actual answer. So for example, here, the remainder, which means the difference between the actual answer and my partial sum that I'm taking, right? I want to know what's the difference between the actual answer and the second partial sum. It turns out that it will always be within the third term, right? Now the A3 in this case is going to be what? It's just 1/3. Right? So S2 is within 1/3 of the actual sum. Which means when we get to the point where we can compute the actual sum, it turns out that S2 actually puts me within 0.33333 of the actual answer. Right? That is, S2 is equal to, what is S2 equal to? If you plug in 1, you actually get -1 plus a half. This is actually -1/2, right? Is within 1/3 of the actual answer. That is, this guy is going to be somewhere between -1/2 plus 1/3 or -1/2 minus 1/3. Right? The n plus first term approximates the nth partial sum. Right? It actually tells you how far apart you are from the actual answer. And this only works for alternating series, by the way, not in general. It's called the alternating series approximation theorem. So there's a theorem that says whatever term you're at, it actually approximates how far you are from the answer if you add up all the terms before that. Right? It's a really neat theorem. And we're actually going to be using that for a while. In a while, probably when we get to 8.5 or 6. So with alternating series, we can actually approximate them within any desired degree of accuracy. So let's say I wanted to approximate what the actual answer is within 2 decimal places. Right? Since Rn equals S minus Sn less than An plus 1, it suffices to make An plus 1 less than 1. Right? If this guy's within 1/100th of the answer, then overall my approximation will be within 1/100th of the answer by this theorem. So this means An plus 1 is actually 1 over n plus 1. This means I need n plus 1 to be bigger than 100. This means I need n to be bigger than 99. Therefore, if we, what did the question ask? How many terms? Therefore, we only need 100 terms to get to within this should have been within, that's background. Within 1/100th of the actual answer. Okay. So a theorem like this is super convenient if, for example, you have a CAS at your disposal, right? You can just tell the computer to, just calculate the first few hundred terms, I only need 2 decimal places, right? And the series is probably really difficult to find in general. Probably it's like this crazy hard limit where you can't tell if it goes to 0 or not. But you don't need to have the exact answer, you just need some approximation with it. You can just do this silly little inequality and solve that. And then tell the computer, just do 100 terms, that's good enough. Right? That we're going to be using later on. So it's a very neat thing that works with alternating series. All right, last thing we're going to do today is absolute convergence. We say a series is absolutely convergent if it converges when we put absolute values around all the terms. Right? If the original series converges but it is not absolutely convergent, it means if I put absolute values it messes everything up. We call it conditionally convergent in that case. Right? So there's a distinction between being absolutely convergent and being conditionally convergent. Example, minus 1 to the n over n is conditionally convergent. Right? Since this guy converges by the alternating series test, but if I put absolute values around all the terms, what happens? I just get 1 over n, which is divergent. So on its own it converges, but if I throw an absolute value in there, it doesn't converge anymore. Right? If that happens, we call it conditionally convergent. It converges on the condition, we just leave it alone. Right? Just let it do its thing and don't bother it, it'll converge. Right? Example. If I made that an n squared, that is actually absolutely convergent. Since I put absolute values around this guy, I would get just the sum of 1 over n squared, which converges. How do I know that converges? P series of p equals 2, which is a convergent P series. Right? So even if I throw in absolute values, this guy still works. Right? Clearly it works with the alternating series test as well. So it converges even with absolute values, we call it absolute convergent. If it converges but it doesn't converge with absolute values, we call it conditionally convergent. If something converges absolutely, it also converges conditionally, right? Absolute convergence is the gold standard of convergence. When you converge absolutely, you converge in every sense of the word, right? So that's another important concept. Absolute convergence, really strong convergence. But because absolute convergence implies conditional convergence, it means if you're testing for one or the other, you can just test for this one first. If this one works out, you don't have to test that one, right? So there are times where we're going to be faced with a question, given these random series, do they converge absolutely or conditionally, or they don't converge at all, right? And when you're faced with such a question, there's a sequence of steps that you should take. Step one is to check for absolute convergence first. Right? Because if you have that, you have the other one. So you don't even need to check it. Whereas it's possible to have the conditional convergence, but not the absolute convergence. Right? So it's best to spend your time checking the absolute convergence first. If it is absolutely convergent, stop. Don't do anything else. Say the series is absolutely convergent. Otherwise, go to step two. So step one, check absolute convergence. If it works, you don't have to do anything else. You just stop and say the series is absolutely convergent. Step two is to check conditional convergence. Which means remove the absolute values that you put there. Unless they were there in the beginning. And if this series converges, stop. The series is conditional. Convergent. Otherwise, the series is divergent. So absolute convergence is the gold standard. Conditional convergence is your last hope, right? If it's not conditionally convergent, it just doesn't converge. Let's see. Let's look at an example. First, these two are examples that I gave you. Right? So you can sort of try to write out what those guys would look like. So notice in the alternating harmonic, if you throw absolute values around it, you get the harmonic series, which means it diverges. So that would be in the case where step 1 doesn't work, so you move on to step 2. Then when you check conditional, you apply the alternating series test. And that one would work out, so you say it's conditionally convergent. If you have this guy, you throw absolute values around it, you get this, which automatically converges, so you stop at step 1. Right? You just say it's absolutely convergent. So there was a similar question to this in the homework, but it was about sequences. What if now we look at the series of that guy? Determine if it's absolutely convergent, conditionally convergent, or divergent. So step 1, check absolute convergence, right? So what does that mean? What do I check? Throw absolute values around it, look if it converges. Okay, question, does that converge? How do you know?
It goes 1 between almost negative, almost 0 and 1, but the bottom part goes to infinity.
Okay, so what does that
So
mean?
it converges to infinity, to 0. 1 over.
The limit of this converges to 0.
Yes.
That doesn't tell you if it converges or not. That's not a p-series, there's a cosine on it.
Why don't you just compare it to 1 over?
You can compare it. Cosine in absolute values is less than or equal to 1. And what do you know about this guy? This is a convergent p-series. This means this guy converges by what test?
Comparison test.
Comparison test.
Do we have to mention what test we're using?
Yes, you always have to mention what test you're using. Therefore, the original series, you would say converges absolutely. Yes, you always have to justify your steps. Now, there comes a point where I don't expect you to prove that it's decreasing or whatever, but you better make sure it's decreasing if you state it's decreasing. Right? But right, sometimes it's just obvious that it's decreasing, yeah. If it's not obvious, you have to prove it. But in general, when you're using a test, I expect you to tell me which test you're using. How do you know this converges or what? I mean, I'll do the alternating harmonic just so you can see an example of something that's conditionally convergent, like written out. So here, you could check absolute convergence, which means you look at this guy, but that's just equal to this guy, which diverges So not absolutely convergent. Right. The harmonic series, you can just say diverges, everyone would know that. Right? And so you go to step 2, check conditional. In which case now I look at the original series. There's a conditional conditional. With absolute values, doesn't work. If I take them away, it works. That you call conditional convergence. Now, here's the funny thing with absolute versus conditional convergence. There are a bunch of theorems in calculus and beyond that will only work on your series if your series is absolutely convergent. And that's because conditionally convergent series are sort of weird. Notice that if you have a finite sum, right, you can arrange the terms, won't make a difference. Turns out when you have an infinite sum, this doesn't work. In the case that you have a conditionally convergent series, it's actually a case where you can actually rearrange the terms and get a different answer. Right? It's sort of weird. In fact, it gets weirder. You can actually rearrange the terms to obtain any answer you want. Right? If you have a conditionally convergent series, you can rearrange the term to obtain any real number you feel like. Right? And that's why these guys are sort of fickle. Right? When you're doing calculus with them, you never know which way they go. If someone rearranges the terms, everything goes to hell, right? So these guys, you can't really do a lot of stuff with them sometimes. However, if things are absolutely convergent, rearrangement doesn't matter, right? You can arrange the terms in any order you want, you'll always get exactly the same answer, right? So that's what makes them really nice. By the way, that's called the rearrangement theorem. There's a theorem called the rearrangement theorem, which basically says just that. If your series is conditionally convergent, then a rearrangement of the terms can obtain any real number. Right? If it's absolutely convergent, you'll always get the same number upon any rearrangement. Right? And that sort of sturdiness of absolute convergence is one thing that's going to be really nice for us, and we're going to be able to use calculus on these guys. So we'll see that next time. For now, we'll end there. We haven't finished 8.4. We just have 2 tests left, which are nice formulas. We'll finish that like early next class.